looking at the central potential problem, and in the last lecture we had reached a point where we could write the radial equation. So let us begin with the radial equation. So here we have a central potential V of r working in spherical polar coordinates, and so we will write the equation for r of r. The entire wave function was a function of r, theta and phi, and that was r of r YLM of theta phi. Now if I did not realize that the potential is an operator acting on r of r, I would write a wrong equation like this. But I should remember that all terms there multiply r of r, and so I have 1 by r squared d by dr of r squared dr by dr plus 2m by h cross squared E minus V r of r minus L times L plus 1 by r squared r of r. This object is equal to 0. Let us look at a simple problem. Let us look at a situation where we only concern ourselves with the ground state of say a nucleus. Since we have just done the shell model of the nucleus, we can look at a problem where we just look at the ground state of a nucleus, and the specific nucleus that I would like to consider is the deuteron. This is a neutron proton bound state. There is one neutron and one proton. Nobody has seen a deuteron in the excited state. We now know that the deuteron exists only in the ground state. That means in the L equals 0 state. So as far as the deuteron problem is concerned, the radial equation simply becomes 1 by r squared d by dr of r squared d capital R by dr plus 2m by h cross squared E minus V of r of r equals 0. What is it that we are trying to look for? Now we will do a very rough calculation, use an effective model, and see if we can explain that for a generic potential, that means without assuming any specific properties for the potential more than is necessary, without going into the details of the potential, we will see if the deuteron is a loosely bound state. By a loosely bound state, we mean the following: that if you take the deuteron and give it a very small perturbation, a small kick, then the amount of energy that is needed to go to a possible excited state is much more than what is needed to separate them. In other words, in a classical picture, if you think of the neutron and proton as hard spheres, that would be a tightly bound state in a classical picture. And since the typical size of the nucleus is 1 Fermi, the center to center distance would be 1 Fermi. This is a crude picture, but it should do the job. Now a loosely bound state is one where you do not expect a situation like this, where they are as close as possible to each other. So you would expect the mean size of the deuteron, the root mean square size if you wish, to be much more than a Fermi. And you would expect therefore that the entire distance from here there is more than 2 Fermi, and then you would say it is loosely bound. The idea is to try to explain why the deuteron cannot be seen in an excited state. So if it is so loosely bound, even a small perturbation, a small kick to the deuteron, a small supply of energy is enough to dissociate the neutron from the proton and separate the nucleus into the neutron and the proton separately, not keeping them as a bound state. Whereas the amount of energy that is needed to kick it to a higher excited state is much more. And therefore, since even a small perturbation would separate the deuteron into a free neutron and proton, that would explain why the deuteron is in a loosely bound state, why the deuteron does not exist in the excited state. So, the idea is to use a generic potential and see if indeed the size of the deuteron, the average size of the deuteron, is much more than 2 Fermi. Then we have some handle on this problem, and that is what I would try to do right now. Now, having set L equals 0, I need to assume some form for the potential. As I said, we should be able to see this without going into great details of the potential. I know it is a bound state, therefore, it is an attractive potential. So, let us say that it goes from minus V naught, but the nuclear force is a short ranged force, and therefore, it drops off to 0 at some point, let me say P. So, this should roughly be of about a Fermi. I am not assuming anything more about this potential. It is a short ranged force and it is an attractive potential. Now, what is the energy? The energy is really the binding energy of the deuteron, and that is the energy that binds the neutron and the proton together. And it is known from experiments that the binding energy is about 2.2 million electron volts for the deuteron. And therefore, this is minus 2.2 million electron volts. I am just going to call this B, binding energy B equals 2.2 MeV. I am not so concerned about what happens in this region. So, somewhere here is B, minus B if you wish, and that is about 2.2 MeV. The point is the following. Here in this region, it is clear that V naught is greater than B. Therefore, this equation would just become minus B plus V naught. Let me imagine that it is not a function of R. Let me imagine that all over this place V naught is a constant and it is greater than B. But then of course, here V naught is equal to B. So, it is some kind of decreasing function or a constant function which gets cut off at that point and becomes equal to B. Not assuming any details of the potential, just using the fact that up to this point V naught is greater than B. And therefore, this is a positive quantity, and that is okay. But then out here beyond R1, for R greater than R1, you can see that E minus V is negative, because V abruptly goes off to 0 pretty fast actually. It is a short range potential, and this object is negative. So, E minus V is negative in this region, and therefore, it is a classically forbidden region beyond R1, because the kinetic energy is negative. So, it is this region that I am really interested in, because in a tight approximation, that is where the neutron and the proton are like hard spheres which are touching each other, the end to end distance is 2 Fermi. Now, I am really interested in how much penetration is there in this quantum mechanical problem into the classically forbidden region. But that is the region where the potential is 0. So, basically I am looking at things here. As you can see, this is a crude calculation, because I am not really worrying about the actual form of the potential. On the other hand, if I can show, even with these minimal assumptions, that the size of the deuteron is much larger than 2 Fermi, then indeed it is a loosely bound state, and one has, as I said, an explanation of why the deuteron does not go to the excited state. So, what is the equation in this region? So, I am only concerned with the equation, the radial equation in the region r greater than r1. So, this is 0. Let us look at this equation in any case and try to write it in a better form. Let me write r of r as some u of r by r. Then r prime of r, prime means differentiation with respect to r, is minus 1 by r squared u of r plus 1 by r u prime of r. And r squared r prime of r is minus u of r plus r u prime of r. I have d by dr of r squared r prime of r, and that is minus u prime of r plus u prime of r plus r u double prime of r. So, 1 by r squared d by dr of r squared r prime of r the u prime cancels out, and I just have a plus 1 by r u double prime of r. So, the first term is just u double prime of r by r. Of course, I should remember when I do this, when I write r of r as u of r by r, I should worry about what happens when r goes to 0 and when r goes to infinity. Clearly, u of r has to behave reasonably for r going to 0 and r going to infinity, because I want things not to blow up. So, for instance, when r goes to 0, I would expect u of r to at least go as r, and so on. In any case, writing down this equation in terms of u double prime of r, I basically have 1 by r u double prime of r plus 2m by h cross squared e minus or minus b plus v naught u of r by r equals 0, and therefore, I have a simple equation like this. I have u double prime of r plus 2m by h cross squared minus b plus v naught u of r equals 0. So, in the region r greater than r1, so let me just write it here. For r greater than r1, my equation is d2u by dr squared minus 2mb by h cross squared u of r equals 0. So, the solution is simple. U of r is e to the minus root of 2mb by h cross squared r. The m here is clearly the effective mass or the reduced mass. In this problem, it is mp mn by mp plus mn. The mass of the proton is approximately equal to the mass of the neutron. So, its mp is approximately 940 MeV by c squared. And that is the same as the mass of the neutron. For purposes of this calculation, we can just substitute mp equals mn. I would even just say this is roughly 1000 MeV by c squared, should do. That is the same as mn. So, you see the length scale in this problem is given here. So, u of r goes as e to the minus r by capital R, where capital R is h cross by root of 2mb. B is the binding energy. It's an experimental input. That's 2.2 MeV. It comes from experiments. M we know. M is just, this is just 1000 by 2, because this is twice MP and that's an MP squared. So I can put that there. And I can substitute for these numbers, substitute for the Planck's constant and find out what's happening. And if I just put in these numbers, and remember that if I set C equals 1, then H cross is about 200 MeV Fermi. So if I put in these numbers, I find that R, which is really the length scale in my problem, and that's why the deuteron has a bound state, this R is somewhere between 3 and 4 Fermi. So that's 4 Fermi. What should have been 2 Fermi, if I think of them as hard spheres, what should have been 2 Fermi across this distance, that's 1 Fermi typically, is really 4 Fermi. And therefore I know that this classical picture is no longer true, and in fact there is a lot of penetration into the classically forbidden region, and the deuteron is a loosely bound state. It is therefore easy to envisage a situation where the smallest perturbation separates the deuteron into a free neutron and a free proton. So this is one situation where I have used the radial equation and tried to explain at a very simple level why an object is seen only in the ground state. And we have not used any particular form for the potential and so on. Needless to say that this can be improved. In fact, you can use a potential which is perhaps in its details more realistic. You could use a potential like this, a hard core, which means no penetration here, so that's an infinite barrier. This is V of R. And then there is a square well here, extending over a certain range, typically say 1 Fermi, and then 0 here. So this is region 3, where the potential is not even there because it's a short range potential. And then there is a region 2, where we can use a square well. And this is region 1. We call it the hard core because there is no penetration here. And of course, you could write down the equation, the Schrodinger equation, in the 3 regions like you're used to doing. And then when you match the wave functions here, remember that this wave function in region 2 should vanish at R equals C because there is no penetration onto this side. Psi 1 is 0. The wave function in this region vanishes. And then here you could match the wave function and the derivatives between psi 2 and psi 3, the first derivative. Go through all the details. You could fit a V, which would, a typical V, which would tell you that it's a loosely bound state. So the root mean square size is much more than 2 Fermi. So you see, you can improve upon the simple model that I started off with. But even with this very simple model, an important feature emerges. And that is perhaps the strong point of such a simple model. Need not go into details to see a very important fact that you can verify experimentally. So that's the deuteron problem. And then by way of a comment, in one of my earlier lectures, I had spoken about the generalized Pauli principle. But I had said that isopartner fermions, this is the generalized Pauli principle, which I did talk about in one of my earlier lectures. Isopartner fermions, example, neutron and proton. They form an iso doublet. Consider isopartner fermions. The total wave function has a space part, a spin part, and an isospin part. And I said that under interchange of the space, spin, and isospin labels, the total wave function must be antisymmetric if you are considering fermions which are isopartners of each other. You will recall that the proton and the neutron form an iso doublet. This has I equals half and I3 equals half, and the neutron has I equals half and I3 minus half. Now let us look at the deuteron. Since L is equal to 0, the parity, the space parity, as you have now learnt, is given by -1 to the L. It is in the ground state, and therefore the space wave function is symmetric, because the eigenvalue of the parity operator, remember that the angular wave function here is the spherical harmonic y 0 0, so the space parity is +1. So the space wave function is symmetric. Now if you look at the spin wave function, yesterday we had looked at a very simple shell model for the nucleus. So you know that the ground state, the 1s state, can be filled with 2 nucleons, and since there is only 1 neutron and 1 proton, they occupy only the s state. This is the 1s half. J is equal to half in this state. Experimentally you find that the spin wave function is also symmetric. So psi space, psi spin is symmetric. That is what you get from here. So if the spin wave function is symmetric and the space wave function is symmetric and the total wave function must be antisymmetric, psi isospin should be antisymmetric. And since these are isopartners, the coupled states that you can have are 1 1, 1 0, and 1 minus 1. The first is the isospin and the second is Iz, and 0 0. You will recall that these are symmetric wave functions, symmetric under interchange of the Iz labels. So if you interchange the Iz labels of the proton and the neutron, the isospin wave function is symmetric, whereas this is the antisymmetric wave function. And therefore, by this token, by this fact that the generalized Pauli principle holds here, the deuteron has isospin 0, which means it has no isopartner. So that is a bit of a prediction that one can make. The fact that the spin of the deuteron is 1 and the fact that it exists only in the ground state, and therefore the space wave function is symmetric, would imply by the generalized Pauli principle that the isospin wave function is antisymmetric, which means that because each of this is an I equals half state, the proton and the neutron, it exists in the isosinglet state. The deuteron exists in the isosinglet state. So as a consequence of the generalized Pauli principle, we now infer that the deuteron exists in the isosinglet state. There is no isopartner for the deuteron. So much for the deuteron problem. Now let me consider the radial equation in a more general context. That means where I do not set L equals 0. So the problem that I would now like to look at is the hydrogen atom. So let us forget this and we look at the hydrogen atom problem. Of course, the angular wave function is YLM of theta phi, because V of r is minus ZE squared by r in general for a hydrogen like atom. the Z would tell you the number of protons. So, so I'll just write it as minus ZE squared by R in general, and it's attractive, so there is a negative sign out there. M is of course the reduced mass between the nucleus and the electrons, because we are looking at an atom here. And therefore, retaining this as well, I can substitute here in this equation as plus ZE squared by R. This is what I have. Now, in order to go to dimensionless variables, which is the way I do these problems, first of all, identify a length scale. H cross squared by ME squared provides me with the length scale. I'll call that A naught. I'll call it the Bohr radius. So that's going to give me a length scale in this problem. I will look for a bound state. There is some point in looking for a bound state now. And then let me define an object alpha squared as minus 8me by h cross squared, because E is negative. E is less than 0 because we are looking at a bound state. And therefore, alpha squared is positive. So, if I put alpha squared as minus 8me by h cross squared, and I define an object lambda, of course, this, as you know, would have dimensions. It has dimensions in terms of length. So, now I define a lambda which is 2m ZE squared by alpha h cross squared. Alpha has dimensions of 1 by length. And lambda itself is dimensionless. H cross squared by me squared has dimensions of length, and therefore lambda is dimensionless. So, in terms of lambda and alpha, I can just rewrite this equation. Let me also do the following substitution, that rho is alpha r, and rho is dimensionless. So, this differential equation is going to be written for r of rho. And how does this equation look? So, r is equal to rho by alpha, and therefore, d by dr goes to d by d rho times alpha, and therefore, this equation just becomes 1 by rho squared. There is an alpha squared on top. D by dr becomes alpha d by d rho. R squared is rho squared by alpha squared. Dr by d rho, that is again an alpha d by d rho r of rho. That is the first term. And as you can see, the alpha squareds here cancel out. I have an overall alpha squared there, and that is all there is in the first term. The second term is plus 2me by h cross squared, and that means it is minus alpha squared by 4 r of rho. That is this term. 2m ZE squared by h cross squared alpha is lambda. Therefore, I have lambda alpha by r, that gives me another alpha out there. So, it is lambda alpha squared by rho minus L times L plus 1 r of rho by r squared, which gives me a rho squared alpha squared. This is equal to 0. Now, let us write this neatly. It's clear that the alpha squared can be cancelled out in every term. And then I have the following: 1 by rho squared d by d rho of rho squared dr of rho by d rho. That's the first term. Plus lambda by rho minus quarter minus L times L plus 1 by rho squared r of rho equals 0. So this is the equation that I have. As always, this is in terms of the dimensionless object rho, and as always I'd like to look at the asymptotic form and see if it is well behaved. So let's see what happens for large rho. Recall that rho is alpha r, and rho therefore goes from 0 to infinity. Now for large rho, what survives in this equation is this: 1 by rho squared d by d rho d squared dr of rho by d rho minus quarter r of rho equals 0. And then you can see that r of rho is essentially e to the minus rho by 2, because it pulls out a minus half in the differentiation, and then once more that gives me a plus quarter, and that's what is going to cancel with this. Quite apart from this 2 rho here, and there's a rho squared there. So it's a simple matter to check that r of rho goes as e to the minus rho by 2. Now look at what happens as rho goes to 0. For rho going to 0, 1 by rho squared d by d rho of rho squared dr of rho by d rho, that term has to be put in here, minus L times L plus 1 by rho squared r of rho equals 0. Now this tells me that r goes like rho to the L. I leave this to you as an exercise. For small rho, this is for rho going to 0. And therefore, I have a particular form for r of rho, that is rho to the L, that comes out of looking at rho going to 0, e to the minus rho by 2, and that's there because when rho goes to infinity it should be well behaved, some L of rho. So basically, as always, I should recast this equation, and write it in terms of an equation for L of rho. I should just change, I should substitute for r of rho as rho to the L e to the minus rho by 2 L of rho, and get a differential equation for L of rho. And if I do that, I leave it to you as an exercise, you will get an equation like this. You get rho d2 L of rho by d rho squared plus twice L plus 1 minus rho dl by d rho plus lambda, and this lambda you will recall is 2m ze squared by alpha h cross squared. Rho itself is alpha r minus L plus 1 L of rho is 0. So this is the equation that you will get. I leave this to you as an exercise. It's a simple, straightforward substitution. Of course, we know by now that the next step is to use a series solution for L of rho. So you would write a series solution of the form L of rho is summation over S Cs rho to the S. But I know the following, that when rho goes to 0, L of rho, I know that r of rho should go as rho to the L. So L of rho should go as some constant. And therefore, S takes values 0 all the way up, in principle to infinity, unless the truncation of series is demanded. So as of now, I know that it starts with s equals 0 and goes all the way up. Substituting this in this equation, I can find out the recursion relation. Do you see that Cs plus 1 by Cs turns out to be this quantity? So these are the exercises that you need to do. No new frills or fancies. The same way in which we handled the harmonic oscillator problem, or even the angular momentum, the orbital angular momentum eigenvalues and eigenfunctions. But look at this. For s going to infinity, for large S, Cs plus 1 by Cs goes as 1 by S. That's an S there and there's an S squared here. But that's precisely the ratio of coefficients in the series e to the rho. So if you expand the series e to the rho and look at the ratio of coefficients for large S, if you did this series expansion, you will find that that goes as 1 by S. And that is unfortunate, because then it tells me that R of rho goes as rho to the L e to the plus rho by 2. And then for rho going to infinity, it blows up. And that's not what I want. As a result of that, I'll have to truncate the series. The series, of course, gets truncated. Notice that S is an integer, goes from 0 all the way up. L is an integer, takes values 0, 1, 2, 3. It's the orbital angular momentum. And there is a plus 1 here, which is very crucial for further discussion. So if lambda is an integer, let's say lambda is equal to n, an integer, when S minus L plus 1 equals n, or S plus L plus 1 equals n, the series terminates. And that's exactly what we want. So after that, the numerator is 0 in this recursion relation. And therefore, you truncate the series when S plus L plus 1 equals n. Now this is a very important matter, because it also tells us the value of n. N can never be 0, because n is 1 plus something. So n takes values 1, 2, 3, 4 up. Now if n takes values 1, 2, 3, 4 up, and there's already a 1 here, the maximum value that n can take, L can take, is n minus 1, because let's assume that S is 0, but L is just n minus 1. So L can take values 0, 1, 2, 3 for a given n up to n minus 1. N is given. So this is how L and n get related. N does not get directly related to m at all, but n can take these values, and therefore L takes those values. Now what does this mean for alpha? Lambda was 2mze squared by alpha h cross squared, and alpha has taken the value n. Lambda has taken the value n. So alpha is 2z by n a0, where a naught is the Bohr radius, h cross squared by me squared. So one thing is clear. Now this means that since rho is alpha r, rho is n dependent. And that's an important difference between the kind of problems that we've seen till now and what we see here. Rho itself becomes dependent on n. Now having said that, what is the energy equal to? Energy is of course quantized in units of n, quantized with the quantum number n, because alpha squared was minus 8m E n by h cross squared. So, you can substitute for alpha squared here and you find E n. And what is E n? E n, first of all, it comes with a negative sign, and that is good because it is a bound state and we do expect that. Alpha squared has an n squared. So, that goes as 1 by 2 n squared, and this is important, times m e squared by h cross squared z squared e squared. So, this is the energy that you have. M is a reduced mass. The energy spectrum here is not equally spaced. N takes values 1, 2, 3. That is a very important thing. The energy spectrum is not at all equally spaced, but as we proceed to higher and higher values of n or large quantum numbers, the levels get crowded. And then for very large quantum numbers, you find that it looks like a continuous energy spectrum. The discrete nature is no longer seen. And this is consistent with the fact that for large quantum numbers, you go to the classical limit. Or the Rydberg atom can be treated classically. That is, when you work with atoms which are highly excited, in a highly excited state, so that the energy levels are, energy is large, very large, sufficiently large for the level to look like it is part of a continuum. And then you have approached the classical limit. Now, having said this, look at the degeneracies. For a given value of n, L takes values 0, 1, 2 to n minus 1. So, basically there is a summation over L equals 0 to n minus 1, but then for a given L, m can take 2L plus 1 values. So, the degeneracy is this summation, but that is n squared. And as you can see, the degree of degeneracy does not depend upon m, and that is a very interesting observation. It turns out that the degree of degeneracy comes only through a counting of L from 0 to n minus 1, and really n is related to L and not directly to m. What are the eigenfunctions like? So, here are the eigenvalues and we need to look at the eigenfunctions. So, let us go back to this equation, and here we will substitute lambda equals n. So, what we get is the following. Rho d2 L of rho by d rho squared plus twice L plus 1 minus rho dl of rho by d rho plus n minus L plus 1 L of rho equals 0. Since the series for L of rho is a finite series, it has been truncated, one would like to see if really this can be expanded or can be identified with one of the special functions, polynomial functions. In the case of the harmonic oscillator, it was a Hermite polynomial, and in the case of angular momentum, we had the associated Lejeune polynomials. So, now here I can do the following. By inspection, I can see that if I make this identification, Q is n plus L and P is 2L plus 1, then the equation is d2L of rho by d rho squared P plus 1 minus rho dl of rho by d rho plus q minus p L of rho equals 0. And indeed, LQP of rho is the associated Laguerre polynomial which is really defined for rho going from 0 to infinity, as in this case. So actually in the hydrogen atom problem, the radial equation turns out to be the associated Laguerre polynomial, which satisfies the following orthonormality property. This is like psi star psi, so it's LQP of rho squared because it's a real function of rho. But then there is an e to the minus rho, rho to the p plus 1 here, integration from 0 to infinity. And that turns out to be this object. So in fact, when I now write down the wave function for the hydrogen atom, the radial wave function, there are two quantum numbers, r, n, l of r, because the polynomial itself is L with two numbers q and p associated with it, and q is n plus 2l plus 1 is p and q is n plus l. So when I just put that in, r and l of r is L qp of rho, and rho is alpha r, and alpha itself was 2z by a naught r. So that's what I have for rho, 2z by n a naught. So rho is alpha r, that is 2z n a naught r. But apart from this, I would have some normalization factors out here because of the orthonormality relation of the Laguerre associated Laguerre polynomials. So this is r and l of r, and I put down the expression here. You can see that this is e to the minus rho r, which takes care of the large rho behavior. Then there is a rho to the power of L, which is out here. So that's an e to the minus rho r, rho to the power of L. And then you have the normalization which comes from here. Substitute for q as n plus l and p as 2l plus 1, and you will retrieve this q minus p factorial to the power of half, because this is like psi star psi, and therefore there is a half. These coefficients, you put this on top and that below, and that's a half out there, and extras. And then of course the L QP of rho. So this is the radial wave function. Of course the total wave function is r n l of r y l m of theta phi. So basically psi of r theta phi in the case of the hydrogen atom is r n l of r y l m of theta phi. Two special functions are involved. Here the associated Laguerre and there the associated Lejeune. Now if you look specifically for the ground state, the ground state has n equals 1, that's the lowest energy state. And since L can only take value 0 to n minus 1, L takes the value 0. And therefore M takes the value 0. So the ground state is psi 1 0 0 n L m. If you substitute those values there, you find that apart from a constant, it is e to the minus z r by a naught. Now you see, this feature is important for the following reasons. The ground state of the hydrogen atom is essentially e to the minus r by a naught. I have said z equals 1 for the electron. I am just looking at the hydrogen atom. So, Z equals 1. And then what is the probability distribution of the radial position of the electron? So, that object is P and L of R, and that's simply e to the minus R by A naught. So, this is just the wave function. So, you are looking at the probabilities. So, e to the minus 2 R by A naught R squared, and this is the probability distribution, and you can see where it peaks up. This probability distribution is maximum at R equals A naught. So, in that sense, we have connected up with something from the old quantum theory, that the Bohr radius becomes very important, and h cross squared by me squared, at that distance you have the maximum probability distribution of the radial position of the electron. And in that sense, certainly we have connected up with some features of the old quantum theory. Those are the question of definite orbits and so on. The attitude in modern wave mechanics, as we are seeing it here, is very different from what there was in the old quantum theory. So, I will stop here, and we will take it up from here. In the next lecture, we will look at a different problem altogether. The whole purpose of this exercise was to show the importance of various scales, length scales, mass scales, and also the machinery of how exactly you solve for eigenvalues and eigenfunctions in function space, and how special functions play a very important role in this context.